Alright, what's up, guys? So, today we're going to be talking about how to find the pH of weak acids and weak bases. So, we already covered in a previous video how to find the pH of strong acids and strong bases, which was very simple. We know that there's 100% dissociation, so the molarity you have of your strong acid or strong base will be the same molarity you have of your H plus or OH minus ions. But weak acids and weak bases are a little more complex than that. So, what is a weak acid and what is a weak base? Well, it's clearly none of the acids or bases listed in this table. These are strong acids and strong bases. So if it does not fall into any of these categories, then it is going to be a weak acid or a weak base. And what makes weak bases a little bit more, a little tougher to deal with is because we know that strong acids and strong bases dissociate 100%. Now, weak acids and weak bases are not like that. They don't dissociate 100%. There's still going to be some remaining product. There's going to be some remaining acid or base at the end of the reaction or when the reaction hits equilibrium. So that makes it a little bit more complex, and we can't just use the concentration we have of the acid or base and plug that into our negative log expression. It takes a little bit more work than that. So the best way to do that is to get an example problem. And the example problem that I have deals with a weak base. It's HNO2. And we know that this is a weak acid because it's not any of the ones listed here. So we know that HNO2, it dissociates into H plus, into the H plus ion, and it dissociates into our NO2 minus ion. And in the problem that we're given, they say that we have 0.250 moles per liter of HNO2. And they're asking us to find the pH of HNO2 at equilibrium, or when the reaction is finished. So to solve that, we have to do an ice table. I know you all remember it from chemical equilibrium. We have to do this thing called an ice table. And if you are not familiar with it, we're going to go over it right now. So our ice table, and let me just draw the table really quick. Our ice table is the following. The I stands for our initial concentration. Okay, the initial concentration. So to get a good understanding of what we have initially, I'm going to draw out a little beaker. Okay, I'm going to draw out a little beaker. And I'm going to label it B because it's before the reaction takes place. And what we have in the beaker before the reaction takes place is we have a concentration. We have a certain amount of HNO2. Okay, we have some HNO2. But we didn't really produce anything yet. We don't have any H plus or NO2 minus because the reaction hasn't started yet. It's before the reaction. So we know that our initial concentration of HNO2, and I'll do this in a white color, is 0.250 moles per liter. And I'm going to kind of make a half line here. And for our product, we have no product to start off with because this is before the reaction has taken place. So we have produced 0 moles per liter of H plus ions, and we've produced 0 moles per liter of NO2 minus. So the C, it stands for the change. What happens when the reaction is taking place? What is the change? So what we know is when this is happening, when this HNO2 is being produced into H plus and NO2 minus, we're losing some concentration of HNO2. So we're losing some amount. We're going to name that X. And for some reason, I can't write it out. There we go. Minus X. Okay, we're going to be losing some of that HNO2 because we're going to be producing H plus and NO2 minus from this HNO2. So we're going to be losing some of our initial concentration of reactant. And we're going to be gaining in the reaction, we're going to be gaining some H plus ions, and we're going to be gaining some NO2 minus ions. So our beaker will start to produce less and less of HNO2 because it's breaking off into more and more H plus and NO2 minus ions. And our E is the equilibrium expression, or what the expression would be like when it reaches equilibrium. So basically, we take our initial concentration and our change, and we'll put that into an expression. So 0.250 minus x. Okay, and this should be ringing a bell from your chemical equilibrium days. Same thing with H plus. We have 0 plus x, which is just going to be x. 0 plus x, just going to be x. And this basically says the basic expression that we have of this reaction when it's reaching equilibrium. We're going to be losing some of our reactant, and we're going to be making more and more product as the reaction goes on. And now we have to write something that we should be familiar with, our equilibrium expression. Okay, our equilibrium expression. And that is going to be our acid dissociation constant, okay, a Ka, it's denoted by Ka, our acid dissociation constant. And how do we find this acid dissociation constant? Well, they should give it to you in the problem, or if they don't give it to you in the problem, it should be in the back of your book. And the acid dissociation constant for HNO2 is 4.0 times 10 to the negative 4. So this is just like chemical equilibrium now. The constant is like the constant just like if we were dealing with gases or something like that in chemical equilibrium. This is just dealing with acids. So the constant we're given for our acid here, HNO2, is 4.0 times 10 to the negative 4th. And of course, we know our equilibrium expression has to be product over reactant. So we have to take our x here and our x here, and we have to multiply it. Remember, this is ringing a bell in chemical equilibrium, so we have x times x, or x squared, and we have 0.250 minus x for our bottom, for our reactant expression. So we can simplify this into x squared, and what I'm going to do in the bottom is something called the 5% assumption, okay? And I'm going to write down just 0.250 at the bottom. And you should already know why I'm doing this, but just to give you a really quick explanation, why I just put this 0.250 is because our constant is so small that we think that the change, this minus x, the amount of HNO2 that's being converted into H plus and NO2 minus is so small that our end result would be very close to 0.250 moles per liter of our HNO2. So we're saying that at the end of the reaction, the loss of HNO2 HNO2 is so small that really we could make the assumption that it's going to be approximately 0.250. It's approximately going to stay the same because this Ka value is so small. So now we just have to do basic algebra. We multiply both sides by 0.250. Okay, and we take the square root of whatever value we get, and we should get x to equal 0.010. Okay, and what I basically did was I multiplied both sides by 0.250, and I got x squared equals whatever that amount is, 4.0 times 10 to the negative 4th times 0.250. I took the square root of that to get x by itself instead of x squared, and it yields the value x equals 0.010. Now, because we made an assumption, we have to make sure if it's a valid assumption, and that's why it's called the 5% assumption. So what we do is we have to divide this x value by the initial concentration that we have of the thing we assumed from. So the initial concentration in this case of HNO2, because we assumed that amount. We used the 5% rule for this specific compound. So we put 0.250 at the bottom, and we multiply that by 100 to get a percent value. And we get about 4%. Now, if the percent is less than 5, we know that the valid's okay. The assumption is okay. The assumption is valid, excuse me. Now, if it's above 4%, that means that no, you are not allowed to make an assumption for this case. You have to actually use some quadratic expressions. But most of the times, the assumption should be valid, excuse me, because the constants are so small. So we know that our x value will be 0.010, and we know that this x and this x, this expression that we created, is what we have to plug in for this value. So we pretty much solved for x. We solved for our H plus concentration and our NO2 minus concentration by solving for x, because that's what our expression is here in the reaction. So now we have our H plus concentration. We know that our H plus concentration at the end of the reaction is going to be 0.010 moles per liter. That's why we solved for X. That's the whole reason why we solved for X, to get that concentration of H plus. So all we have to do now is we have to take this X value. We have to take this X value because that is the H plus concentration, and I'll write it down here. Our H plus concentration is equal to X, which is 0.010. It's equal to X because of this expression here. And we just take the negative log of 0.010 to get the pH, because what is pH? It's the negative log of our H plus concentration. So our H plus concentration is 0.010 moles per liter. We plug that into our equation, and we should get a pH that equals approximately, and I'll write it up here, a pH that equals 2.00. So that is how you get your pH of a weak acid. You have to use the ice table method, and you have to have an equilibrium expression, which I kind of outlined how to do that. You're going to be given your Ka value. Most of the times you're going to be given your Ka value. If it's a homework problem or something, it should be in the back of your book in the appendix. And by getting your Ka value, you simply solve for X. And because you came up with an expression that H plus, the concentration of H plus ions, is going to be equal to X, you know that the 0.010 moles per liter is going to be your molarity of your H plus, and your molarity of your H plus, the negative log of that, is going to give you your pH. I may have to cut this video short and make a separate video for weak bases, but it's essentially going to be the same method with just one extra step. Thank you for watching, and I hope you enjoy.